In this video, we use an equivalent circuit to solve for a current in a load resistor. In this circuit here, this 1 ohm resistor, this is our load resistor connected between the nodes of interest, nodes A and B. And we want to use an equivalent circuit to find what the current through that 1 ohm resistor is. So I'm going to start off by finding R Thevenin, and this time I'm going to use R Thevenin, or I'm going to find R Thevenin by the R equivalent method. So as we talked about before, if you remove the load and eliminate the independent sources, okay, you kill them. I killed this voltage source with a short, and I killed this current source with an open. Well, now if we find the REQ from the perspective of the load, that is R Thevenin. Okay, so you start with these two resistors that are in series, and then those two 6s in series is in parallel with the 4, so this is just going to be 12 in parallel with 4. 48 divided by 16 using product over sum, so that's our R Thevenin. Okay, 3 ohms. Okay, so we have R Thevenin. Now we're going to find V Thevenin by removing the load. Okay, so we remove the 1 ohm resistor, and now calculate what the voltage across that open is. Okay, once the load is removed, if you find the voltage across where the load was, okay, that's the Thevenin voltage. Okay, because again, Thevenin voltage is equal to the open circuit voltage between the nodes of interest A, B. So to calculate that voltage, I use node voltage method. I made this bottom node ground, okay, which is node B. And this node here is known, right? There's 18 volts at this node with respect to ground. So that means we just have an unknown node here that I'm going to label C, and then an unknown node here, which is node A. And once I find the voltage at node A, that is our answer, right? Because once I find the voltage at node A, it's that voltage at this node with respect to ground, which is across the open, right? Which is what I'm after. So I'm going to set up a node voltage expression here at these two nodes. So I had this current here that I labeled I1. The 3 amps is already defined for us going into node C. I called this current here I2, and I called this current I3. Okay, so KCL at C is just going to be I1 plus 3 amps equal to I2. KCL at node A is just I2 flowing in equal to I3 flowing out. Okay, now we write the currents in terms of voltage using Ohm's law. So I1 is going to be 18 minus VC over 6. Okay, then the plus 3. And that's going to equal I2, which is going to be VC minus VA over 6. Okay, then here, I2 again, VC minus VA over 6. And then I3 is just going to be VA minus 0. Because remember, we made this bottom node ground, so VA minus 0 over 4. Okay, so there's your two equations, two unknowns, and we're only interested here in VA because again, that's our answer for the open circuit voltage. So when I solved this, I just solved for VA, and I got an answer of 9 volts. Okay, so VA, that is the open circuit, and again, by definition, that's the Thevenin voltage. Okay, so we have our equivalent circuit values for our Thevenin equivalent. So here they are. So this is what we just determined. V Thevenin 9 volts, and then earlier we got R Thevenin 3 ohms. So now to find the current through the load, the 1 ohm resistor, using equivalent circuit, I now connect the 1 ohm resistor between nodes A, B of the equivalent circuit, and all I have to do is find this current flowing in the series circuit, and that is the current through the 1 ohm load. So that's just a very simple Ohm's law, that the current for the load, the 1 ohm resistor, is just going to be the 9 volt source divided by the total resistance in the path. So 2¼ amps, that's our answer. So again, this is the beauty of equivalent circuits, is that once you have your equivalent circuit, to find current, voltage, or power for the load, it's a very simple analysis. Now, as a bonus, let's say you're asked, well, what is I short circuit? Okay, remember, I short circuit, that would be the current that's flowing through a short connected between AB. Now, to find that current, we could go back to the original circuit, and we could do either a mesh current analysis or a node voltage analysis to find what that current through the short is. But since we have the equivalent circuit already, it really would not be very smart to go back to the original circuit, because I can just take my equivalent circuit right? Because remember, these two circuits are equivalent at nodes A, B. So instead of finding the current through the short in this original circuit, which would be a lot more work, I can just put a short between nodes A, B of my Thevenin equivalent. And look, it's just a simple Ohm's law calculation, right? Just 9 volts divided by 3 ohms. So you see, I short circuit is 3 amps. Also, another way we could get the same answer is we know that R Thevenin is equal to V open circuit divided by I short circuit, right? So therefore I short circuit is just VOC divided by R Thevenin. So you see, we can also just plug in 9 volts over 3 ohms here, and again it equals the same 3 amps. So again, the point is that once you have the equivalent circuit, it's very easy now to find anything about the load, even if that load was a short, right? Because essentially that's what we did here, is we replaced the load resistor with a short in our equivalent circuit to find I short circuit. You could have also solved this problem by doing a Norton equivalent. Actually, let's write that real quick here. Right, the Norton equivalent for this problem would be a current source of value I short circuit, so 3 amps, in parallel with the resistor, with that resistor is R Thevenin, so this would be a 3 ohm resistor. Okay, and we would get the same answers if right, if you put a 1 ohm resistor here, right, you would find that you get the same answer for the current through the load as we did previously.